Last time we introduced the determinant, and in the end we said that if we have two square matrices, if they're in the same dimension, the determinant of the product equals the determinant of A multiplied by the determinant of B. So using that, we can actually think about the elementary matrices we talked about. So we had three elementary matrices. The first one is we have there was one thing I wrote wrong. So the second one I said row replacement, but actually like when we are doing column vectors. So instead of row replacement, we're actually doing the column replacement. Yeah, because these two are column vectors. We're substituting columns here.
Oh, I see.
Right. Okay, so for the column swap, if we have so basically we know that the elementary matrix for column swap is when we have an identity matrix, but at the place I and j, we have 0 for II and 0 for jj, but for ij and ji there is 1. Okay. And so this is our column swap.
Wait, what do you mean with that?
So this was our here when we were doing row exchange of the row operations. So we can we said all the row operations can be represented by the elementary matrix multiplication. So if we want to do row exchange, we can actually, so in the 2D case, we can do 0, 1, 1, 0 to swap the first and the second column. So then if we have this one and we're multiplying by a matrix, say 1, 2, 3, 4, or let's say any A, B, C, D.
Yeah.
So that would give us C, D, A, B. So basically we swapped two rows. We're doing row exchange by this yeah.
So it's just like the inverse. No, not the inverse, but like the reverse of the identity matrix.
Yeah, in this case. But if we have like three, the identity matrix looks like this. But if we want to switch, for example, the second and the third row, then we would have 0, 1, 1, 0 here.
Oh. Oh,
So,
okay.
yeah, this is a column swap, the row swap. But if we multiply the matrix on the right, so for example, if we have A, B, C, D here and 0, 1, 1, 0 here, we will get B, D, A, C. So this is the column swap if we multiply, if we do AE instead of EA. Yeah, so here, when we do, when we talk about the determinant properties, when we do this column replacement, we are talking about we have a E here, and AE is what we want to do for a column replacement or effect. is column replacement. Column swap. And we know that determinant of an identity matrix with just one column swap is the negative of the original determinant. So the determinant of E is actually the determinant of I, but with negative. And we know the determinant of I is just one. So determinant of E is -1. All right, and AE, we know the determinant of AE in this case would be negative of determinant of A. Because we just multiply -1 to the determinant of A. So similar, if we are doing the column scaling, then we're talking about using a matrix and change one of the entry on the diagonal to alpha. And our determinant of E in this case would be alpha because it's alpha multiplied by 1. And determinant of AE in this case is alpha A. Alpha determinant of A. All right, the last one, we have column replacement. We have a matrix from a identity matrix. But at ith row and jth column, we have a alpha. So this is the column replacement. And this case, we know that this is triangular. So if alpha is on the bottom, then it's lower triangular. If it's like on the top.
Oh, your voice is quiet again.
Yes. I'll move closer to the mic. So if the alpha is on the top, then it's upper triangular. So we know that to calculate triangular matrices, we just need to multiply the main diagonal entries. And in this case, it would be just 1. So determinant AE would just be determinant of A.
So column replacement is a triangular matrix.
Yes. Because this is the case where we have i's everywhere, but in this case, jth row and ith column is the alpha. This one is to replace row J with this.
Mm-hmm. Oh, I see.
Mm. And then we know this is a triangular matrix because everything here is 0.
Mm.
Right. Right. So another theorem, we say if we have a determinant of A, if we know determinant of A, then we would also know the determinant of the transpose of A because they will be the same. So we can actually add another column here. And we can talk about the determinant of transpose of ET. All right. So transpose, we would just have this one from the ith row jth column to the jth row and ith column, and this one from jth row and ith column to ith row and jth column. So this one would actually wouldn't change. The transpose and the original matrix does not change. So the determinant stay the same. Okay, and similar for this, because alpha is in the main diagonal, so the position of the main diagonal doesn't change because the I comma I, if we swap them, it's still I comma I. So this one keeps as alpha. Okay, and the determinant of ET. So if the original place is upper triangular, then now this would become lower triangular. And if the original one is lower triangular, then after the swap, it will be upper triangular. So again, the determinant, we just do the product of the diagonal entry. It will still be 1.
Because the diagonal doesn't change, right?
Yes.
Okay.
Okay, so from here we can see at least the elementary matrices, they have the same determinants.
So, okay, I understand the first and the third one, why the determinant of the transpose doesn't change. Because like the first one, the volume is the same, right? Because it's like it's just like flipped around another. But for the scaling,
Mm,
because I thought the determinant, if the determinant is a scalar
mm,
and you scale something,
yeah.
doesn't the diagonal change? Or
Yes. So for example, if you're scaling this original matrix A, and now after the scale, your new volume will be alpha A instead of just alpha. I mean, instead of just A.
oh wait, no, sorry, I meant for the E transpose.
Mm-hmm.
For E transpose, when you like why would it just be alpha on the elementary matrix?
Because this determinant of E means you're scaling it from 1 to alpha. So after the transpose, you're still doing the same thing. You're scaling it from 1 to alpha.
So
So the one you're talking about, like this is a scaling, it's because you think it's a scale of the identity matrix, right?
mhm.
So the identity matrix was multiplied by alpha. And since the determinant of identity matrix is 1, so we are actually doing alpha times 1. So this determinant is 1 times alpha equals alpha.
And then if you did, because this is, oh, okay, I think I got confused between the row swap and the row scaling.
Mm,
Because now these are column operations, but the ones we did before were row operations.
yeah, but
But
it should be the same.
right?
Yeah. Because you actually scaled it. You scaled it from 1 to alpha now. So the determinant of E is not 1, is alpha.
Yeah, I understand that part.
Mm-hmm.
Um,
And
'Cause
same,
because you're finding the determinant of the matrix E, right? So the one post transformation.
mm,
So
the transpose is to swap rows and columns,
yeah.
right? So since alpha right now is on the diagonal, the index would of it will be like a k comma k,
Mhm.
and then the transpose of this matrix would be the same because you just swap the row and column. The alpha would stay at the same place.
Oh, because is it a square matrix?
Yes.
Oh, okay, I didn't get that. Okay.
Right. So since the matrix doesn't change, the determinant wouldn't change.
Oh, okay, okay, now that makes sense.
Nice. Right. Remember, we can only calculate the determinant of a square matrix.
Mhm.
Right.
Yeah, it's my bad.
No problem. Okay. So we know that now because of this theorem, we know if we have a matrix A, we know the determinant of A equals 0. Then we will know the determinant of the transpose of A would be 0. So that means determinant of A equals 0, we know that is the same thing as saying A is not invertible.
Yeah.
So if A is not invertible, the transpose of A also have the determinant to be 0. So we can know that the transpose of A is also not invertible.
Mhm. I see.
Mm, okay. And then we can actually define determinant of A rigorously. We use the column, but I mean we use volume to introduce it, but actually the way we compute it, we have a more rigorous way to define it. So let's define determinant. All right. So right now I have a matrix. So let A be n by n.
Mhm.
And we know we can write it as A11, A21 all the way to AN1. And A11, A12 all the way to A1n. So diagonal would be all the way to ANN.
Mhm.
All right, so let's say each column, each volume vector, we call it V1, V2, all the way to Vn. So then that means for each V, Vk at the kth column,
Mhm.
that equals
A
A1, great, A1k all the way to ANK. All right, now we have
isn't it
vector,
AK1?
uh, NK, 1k to NK. Wait.
Isn't it
Wait.
K?
Hmm?
I thought it was because
Oh,
it
right, kth
yeah, yeah,
column. You're
yeah.
right. Wait, no. The first entry is the row, is which row it is. So you can see here, whoops. This is A12 in the second
Oh
column.
yeah. Oh yeah. Yeah.
Yeah. All right, so I have this vector, and based on basis, we know this vector can also be written as A1k as the factor multiplied by E1
Mhm.
plus A2k multiplied by E2 all the way to ANK. Multiplied by EN.
Yeah.
Yes. Great. Now we can rewrite this determinant of A. So determinant of A would be equal to the determinant of these vectors, V1 through Vn. And for the first vector, we know it can be written as, so this is like a sum of different things. So we can write it as the sum of A let's say AJ1, AJ comma 1, EJ. Because this is the first vector.
AJ comma 1.
Multiplied by EJ.
Is it not? Is it not column vectors?
Yeah, it's the first column vector.
Isn't it the first? Oh yeah. What? Because if VK is A1K to ANK, shouldn't VJ be AJK to ANJ?
Yes, but that's the kth volume, kth column. Right now we are doing the first column. So this K is 1 in this case.
Oh wait, you're breaking it down more.
Right. Yeah, kind of.
Oh, okay.
So J in this case is from 1 to N. Okay. Now we can, so we know the sum, A is just a vector and E is a vector. And when we're doing the determinant, if we're doing a factor multiplied by a vector, we can factor the factor like outside of the determinant calculation. So that means we can write this as the sum of J from 1 to N A J1. All right, on the inside, I changed the first one to J. Let's say it's also J1. And then we're left with from the V2 to Vn. Right. So follow the same step. We can also break the V2 through Vn out. So we would have be, this is our first basis. And this is like a subscription of J. So we have this first sum, the first J from 1 to n. And then we will have another sum, also J, but for the second vector, 2 from 1 to n. So we would have different sums all the way to J sub n from 1 to n. Okay, so that's the sums. And then we think about the factors. So we would have the factors. The first one is aj, comma 1. And then the second one would be aj, comma 2, all the way to aj, comma n. Okay, then we have the third part that we are actually calculating determinant. Okay, we have a determinant of e, j1, e, j2, all the way to e, j3, jn. Okay. Now, so since right now we have, we are calculating a determinant of ej's, and then we know that basically if the j, if we have same ji's, then we would be in the situation where we have like two same columns, and then the determinant would be 0. And for the sum, the cases where determinant is 0 does not doesn't change anything because we'll be adding the 0. So what we really care about is when ji's are distinct. So only. Okay, now basically what that means is j1 through jn should include all the numbers from 1 to n. So these cannot be so since there are n of them, and we want each one to be distinct, so one, like there will be one of which, that's like the pigeonhole theorem. Okay, so then we know that j1 through jn should be include all numbers from 1 to n. But we don't know the order. Okay. Now,
wait, isn't that a given?
what do you mean?
Like, of course, J1 and Jn should span 1 to n.
Um, but so example, like in this case, we so in this case, for like when we are doing the sum, we need to consider like each case where J1 through Jn, right? Basically, that means there could be one case that J1 equals 1, J2 equals 1, and all the way to Jn, they all equals 1. So that means we're only considering E1, E2, the second one is also E1, and all the way, we have basically n E1s. And in this case, our determinant will be 0.
So basically, so for example, if you have, so are you saying like if you have like multiple rows of the same value, you only like you just go back to the first instance of that value appearing?
So actually, this is like a representation issue. So for example, this one actually represents, I need to go over each case for Jn. So the first case would be J1 equals 1. Let's say all the Ji's equals 1. And then then the second case could be all the Ji's equals 1, but the last one, Jn equals 2, like this. And I also have a case where, so all the J1s again equals, for example, 3, but let's say J2 equals 4. So the number of cases here is actually, I think, n to the nth power, but I'm not very good on probability. But okay, I think.
Oh, okay. So it's like every unique set of values, but like inclusive of number, like including number, like I don't know how to. Okay, but
Right. But like when you write a computer program, you will have like 3 for loops and each one, and not 3 for loops, but like n for loops. And
yeah,
for each for loop, you're going through 1 to n. So that's like a I don't know, nested, super nested for loop. Right. So and this is too crazy, but like this one is already enough for us to calculate for a computer program to calculate the determinant of any matrix. But if we want to calculate otherwise, we want to reduce it. And we notice that there are cases like as long as we have 2 columns that are the same. So for example, if we have 2 columns here, they're all doing e to the e2 and e2. Then we know the whole determinant is 0, and we don't need to like it's making nonsense to add a 0 to the equation. So then like after this observation, we basically know that if we actually want to add something, we want at least Ji through Jn are distinct. That means they cover the whole like 1 through n.
like by 1 through n, do you mean rows or like numerical values?
Numerical.
Oh.
Right. So basically, like you were right, J1, for example, would cover from 1 through n because we're adding them from 1 through n. But at the same time, we don't know if EJ1 and EJ2, they are the same one. Because EJ2 is another vector.
Yeah.
Right.
Mm. So is the determinant, when you're calculating the determinant, you're meant to go through every single possibility?
Mm,
No.
kind of like that, but I'm actually just going through every volume vector. I mean column vector.
Right?
Yeah.
What I thought.
And for each column vector, we can further decompose it to a factor multiplied by n standard basis.
Yeah.
Like n factors multiply standard basis. Yeah. As the sum of them.
Because you're basically you're deconstructing a column into this thing times like the elementary, like a column in the elementary matrix, right? Or
Mm,
whatever it's called, like the E.
mm.
So yeah, I guess I just got lost in the
In the notation, it is
I,
confusing. Mm,
yeah, I don't mhm. So
yeah.
basically for determinants, you can't really calculate it by hand efficiently.
Uh, that's why like keep simplifying it. After the simplification, we can actually calculate by hand.
Okay.
If the matrix is not like too big, like 10 by 10 or something, well, we
Mhm.
can still calculate it, but it just need more time.
Okay.
Now we know that we want at least all ji's to be numbers from 1 to n, but we don't know the order. And in cases that we don't know the order, we we introduce like permutation. Have you
Mhm.
heard permutations?
Yeah, it's like the factorial, right? Like every single possibility.
Right.
Yeah.
Um so we have a set of numbers, we don't know the order, so the number of possibilities of different orders will be the k factorial. Great. Okay. Um so let's say this one means a permutation from 1 to n. Set 1 to all the way to n.
So n factorial. And
Oh, this is just a exclamation mark, but
oh, okay.
yeah, but there will be a factorial of them. All right, now we can write the determinant of A actually equal to the sum of sigma, where sigma is a element belongs to the permutation of n. Sigma is not a number, but sigma is like a combination from the permutation of n. And
Oh.
basically, I have the factors. The first factor is the first in the sigma 1, and the second is the second the sigma 2, all the way to alpha sigma n comma n,
Uh-huh.
and
Oh.
E sigma, the first element in the sigma, and then E the second element in the sigma, all the way to N.
So you only take one element from the permutation of each, from each combination in the permutation of n,
Right,
one element.
right. But actually, like combining them is the whole combination, like, for example, first combination of the from the sigma, from the permutation set. So we will see a example fast.
Okay.
Hey, but before that, we still need to introduce something. So you already know the permutation. So it's another number. So we introduce the set some definitions. The first one is the set of permutations of 1 through n. We write it as perm n. And that's basically, for example, a set including the set of 1, 2, 3, all the way to n. And there are things like 2, 1, 3, all the way to n. And stuff like that. And the cardinality of a set basically means the number of elements in the set. Great. So the cardinality of the permutation of n equals n factorial.
I get.
That's great. So this is the cardinality. All right. And then that's our first definition of permutation. The second definition is inversion. So we say an inversion of a permutation sigma is when I is smaller than j, but sigma I is greater than sigma j. Okay, so sigma is one element from the permutation group. So for example, if we have a set 1, 2, 3, 4, 5, 6, and one of the sigma is 1 map to 3, 2 map to 1, 3 map to 4, 4 map to 5. Let's ignore the 6. 5 map to 2. All right, so this is my sigma. And the inversion of the sigma means if I have a lower position, but in this lower position, I have a higher number than the next one, for example, in this case, I have 3 is greater than 1, where 1 is smaller than 2, but 3 is greater than 1.
Mhm.
All right, and I have 3 is greater than 2. In this case, j is 5 and I is 1. And I also have 4 is greater than 2. So when I is 3, j is 5. And I have 5 is greater than 2. Okay, so I have 4 cases where um where I- where there exists an inversion. You hear the firework outside?
No.
Oh, great. Perfect.
Okay.
All right. So then that means the number of inversion in this permutation is 4.
So are I and J just the indexes of combinations in perm n?
Yes.
So in that case, sigma I is 1, 2, 3, 4, 5. Sigma J is 3, 1, 4, 5, 2.
Mm, so sigma 1, for example, is 3. Sigma
Uh-huh.
is like the map.
Mm-hmm.
Yeah. And sigma 2 is 1. You can think of as a map, or you can think of like a Python list.
Yeah.
Yeah, and this is like the index of a list or something.
Yeah, but for like 3, then sorry, can you just go over the 3 is greater than 1, 3 greater than 2 part again?
Sure. So basically, this is like a for loop. So for I in 1, 2, 6, and for j in 2, okay, 1 to 5, 2 to 6. Okay. And basically we want I is smaller than j.
Mhm.
So if I is smaller than j, then we check the sigma. So sigma is the list here.
Mhm.
So if I is smaller than j, sigma I is greater than sigma j. Then we return the inversion number plus 1. Then we have seen an inversion. So inversion plus equals 1.
Why is J from 2 to 6?
Um, be, uh, because well, we can do 1 to 5. I mean, we can do 1 to 6 for both, but since 1 is smaller than j anyway, so j would never be 1.
Mm, I
Because
thought the
Mhm.
I thought the global set though, like the numbers involved would only be from 1 to 5 in total.
Yeah, but Python like 1 to 5 means 1 to 4. It will go through 1, 2, 3, 4. 2 to 6 means it will go through 2, 3, 4, 5.
Oh, I don't know why I didn't think that. Okay.
Right. Because when I equals 5, I would never see a j is greater than 1. So I just ignored it. And same thing for this. Yeah.
Oh, it's what?
Other questions?
No.
Not yet. Good. So this is when we talk about a Python list, but we can also think sigma, like any permutation, as a map. So sigma is one of the permutation and it maps 1 to 3, 2 to 1, 3 to 4, and that. If we think of it as a map, then um basically we're talking about a bijection map because each number in the input, we can find a number in the output to match. And basically no two numbers map to the same thing and no numbers in the output set is not hit by a number in the input. Okay, so and then so this is the definition of inversion. All right, after the inversion, we introduce the sign of sigma. So the sign of sigma, we define it as -1 raised to the number of inversions.
Mm-hmm.
Okay, so in our example case, the sign of sigma in this case is, since we have 4 inversions, we will do -1 raised to the 4th power, we'll get 1.
Uh-huh.
Right. Okay, that's some definition added for our definition. Okay. So we know that since we have a this matrix right here, we know that it should be a permutation of 1 through n. And so that means this is very similar to the identity matrix, but with some permutation going on. So, and a permutation of columns is basically some column column swaps. So we know this is say here. So here we say it's related to I.
Mm-hmm.
By some column interchanges. Or column swaps. Okay, so that means the determinant of this thing is either +1 or -1.
Mm-hmm.
Okay. This equals +1 or -1. Okay. So, and since we define the sign of sigma, we say this this +1 or -1 is defined by the sign. So we claim that the part sigma, the part E sigma 1 all the way to E sigma n equals the sign of sigma. Okay, because the way we define inversion is basically so the number of inversion is basically how many numbers we did. or we would have 1 through 5 without any number greater than a index with a greater, like to a number with a greater index. So the number of column exchange should be matched with the number of inversions we're doing here. So that means if we're doing like odd number of swaps, then we would have -1. If we're doing even number of swaps, then we would have a +1 for the determinant.
Okay. Okay.
Okay.
Oh, wait, that makes sense. Yeah.
Great. So then we can rewrite our definition to determinant of A equals, so same thing, sum of the permutations of n, and we have the factors sigma 1 1 all the way to sigma n n. Okay, multiplied by the last one, we just use the sign of sigma. Okay, so this is our final definition, and let's do an example using it. So right now I have a matrix 1 2 3 next to 1 0 4 1 2 1. So before we know how to find the determinant, we basically do a bunch of column operations, column operations, and keep an eye on the determinant of the column operations. And then after we get to a triangular matrix, then we know how to calculate the determinant. Try. But now with the definition of determinant, we can actually find our main goal. So our goal is of finding this determinant.
Wait, sorry, your voice is gone again.
Weird.
Hello?
Hello?
Hi, hello.
Oh.
I hear you.
Okay, hear me now. Cool. All right. I guess it could be the Zoom is trying to keep the noise outside about the fireworks down, and so it also made my voice.
Oh yeah, that makes sense.
Clear. That's my guess.
I see.
All right. So right now I have a determinant of A, and I want to calculate it using what we just had. So I would first find the sum of permutations, and in this case, our n would be 3 because we have like we are in the space where we have a basis of 3. And the first factor is sigma 1 1. The second is sigma 2 2. The third is sigma 3 3. All right, and then I would multiply by sine sigma. Okay, So we have 3, like our n equals 3. So we would have, if we just do the factorial, we will have 6. We will have 6 permutations.
Uh-huh.
So 6 mutations. First one is 1, 2, 3. Second is 1, 3, 2. Third is 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Right.
Mm.
All right. Now let's calculate the corresponding number for each permutation. And so in the end, we will just do the sum.
Okay.
Okay, so first one, it basically means we
So this
want
is really impossible to do for any number, for like any number bigger than 4.
right.
Okay.
And after that, we will introduce a cofactor expansion where it's easier to do. But still it's not
Hmm.
as easy as just using a computer programmers.
Yeah, I see.
Right, now we have 1, 2, 3. So basically that means the first one is A11. The second factor is A22.
Mm-hmm.
Third is A33. And we have the sign sigma. And in this case, since we do not have any inversions, that will be multiplied by negative 1 raised to the 0th power. All right. Now this would be equal to A11 is 1.
Mm-hmm.
A22 is 0. A33 is 1 multiplied by 1. So we have 0 for the first case. Right. Similarly, for second, we have A11, A32, A23 multiplied by negative 1 raised to, now I have one case where 3 is greater than 2. So you can actually see that basically means we have a column swap of the last 2. So that's negative 1 raised to first power. Okay. So again, A11 is 1, A32 is 2.
And
2,
4.
3 is 4, great. Multiplied by negative 1. So negative 8. All right, same thing for the third one. I'll just say it's 2.
Okay.
The fourth one equals negative 6. Fifth equals 8.
Isn't there only one
Hmm?
for number 3? 2, 1, 3. Isn't there only one inversion? Because 2 and 1 is one inversion.
Yeah,
Oh wait, oh
Mm.
yeah, that's negative. Ignore me.
cool. Yeah, one swap is negative, 2 swap or 0 swap is positive.
Yeah.
All right. So 3, 2, 1 is 0. Okay. Now we just sum this up. So the determinant A, it's to sum of like all i's I just had. And I get the whole determinant of A is 4.
Mm-hmm.
I mean negative 4. Okay.
Oh. So the way it plays out is you really are just choosing one element from each column. Oh yeah, that makes sense. Oh, okay, I see. What? Okay. Why did they write it like that?
Right. But like there were actually many cases where I have the first column and twice the second columns. But since that would definitely equal to 0, so we eliminated those. And then after the simplification, I will have one column at once. Okay, so actually we can conclude some method that helps us in the future. So if I have a 3 by 3 matrix and I want to calculate determinant of A, and if the matrix is written by A11, A21, A31, A2, A12, A13, A22, A23, 32, A33. All right, so this is my matrix and why I want to calculate the determinant. So I can actually, so we know our first case was to just do 1, 2, 3. So
Yeah.
that's like right here. And in this case, it is positive. Okay, so let's say we have a 1, 2, 3, and we want this to be positive. Okay, now I have 1, 3, and 2. So that's 1, 1, 2, 3, but a 3, 1 here. So what we do is actually we copy down the first two columns. So we write down A11, A21, A31, A2, A12, A22, A32.
This is if you want the diagonal to be positive.
Yeah, because we observed that it is actually positive.
Oh,
Yeah, because the permutation doesn't change no matter how our matrix changes.
yeah.
Right. So our second case right here is actually 1, 1, 3, 2, 2, 3. So that's 1, 1, 3, 2, and 2, 3. That's here. And we know that's negative. So 1, 1, after we copy that, we can actually draw a line like this. And we know this is negative. All right, same thing for the third one. We have 2, 1, 1, 2, and 3, 3. Okay, and this was positive because there was a negative number in the multiplication, and then but the sign was a negative number. So 1, 2, 2, 1, 3, 3 is negative, and same thing for 3, 1, 3, 1, 1, 3, and 2, 2. 3 column exchanges. So this will be also negative. So we have like 3 negatives going to the left, and we will have same thing, 3 positives going to the right.
3, 1, 2.
Okay, so then when we calculate a determinant of a 3 by 3 matrix, we can draw this diagram and multiply all the entries that are in the same slashes I was drawing, and then adding in blue or subtracting in green.
Your mic is muted again. Maybe I think it might be like a distance thing. Cause like maybe the computer thinks if you're too far away, then your background it like slots it as the
Move
background.
my mic closer. Okay. All right, so this is for 3x3 matrices. And for 2x2, we have a very similar pattern. Example, if we're having a 2x2 matrix A that equals A11, A12, A21, A22. Okay, and by definition, we know the determinant of A equals the permutation of 2. Right, so for each permutation in the group, we're doing a sigma 1, 1, a sigma 2, 2. And the sign of sigma. All right, so we know the permutation of 2 is just either 1, 2, or 2, 1. And basically, so if you're doing a 1, 1 and a 2, 2, then it's a positive. Then if we're doing a 2, 1 and a 1, 2, then it's a negative. So the determinant of this is actually A21, A22. It's actually similar but easier. So if we're going to from top left to lower right, then it will be add. We're doing the other way, it will be subtract. So the determinant of A actually equals A 1, 1, A 2, 2, subtract A 1, 2, A 2, 1. So if A is n by n, then we use this notation A JK to denote a matrix that's n minus 1 by n minus 1. Where we cross the jth row and kth column. Okay, so that means if I have a matrix A, and it looks like 3, -1, 1, 0, 4, 2. All right, then A comma, A3 comma 2 means we cross the third row and the second column. And what is left is 1, 2, 3, 1.
Mm-hmm.
And this is AJK. And the cofactor means there is a corresponding cofactor for this matrix. is -1 raised to the power of j plus k multiplied by the determinant of ajk.
Oh.
Okay. So for example, in this case, the C3, 2 means I will do -1 raised to the 5th power, and then I find the determinant of 1, 2, 3, 1. Okay. 1, 2, 3, 1 is 1 multiply 1 subtract 6. So it will be -1 multiplied by -5 plus 5. Yes. All right. So with this definition, we can come up with the theorem. All right, this theorem is called the cofactor expansion, where if we have a matrix n by n, then we can get the determinant by either expansion along the row j that means, all right, so determinant A, if we expand through the row j, then basically we consider like the cofactor in each column. So we basically through the jth row, we cross each column and sum this up to find the determinant of A. Okay, and so same thing. So we can pick any row j, and same thing. We can also do an expansion along the columns. So. So if we're doing an expansion along the column K, then very similar, we can calculate the determinant of A to be sum of m equals 1 through n A m k to c m k. Instead of using k here, let's use I or something. All right. All right, now we do a quick example. So if we're doing a 3x3 matrix, same matrix 1, 0, 2, 3, -1, 1, 0, 4, -2. Okay, if we expand along the first row, then we know my first term is AJI. So that's 1 multiplied by -1 raised to a power of 1 is 2. And then what we have left is -1, 1, 4, -2. Okay. Then, so that's my first term. Then my second term, we can do the second column where we have 0 as the first term. And then -1 raised to 1 plus 2. And then what I have left is 3, 1, 0, -2. Okay, and the third is plus 2 multiplied by -1 raised to 1 plus 3. Okay, and I have 3, -1, 0, 4. All right. And now it will be equal to 1 multiplied by 1 plus 2 subtract 4 is -2. And then I have 2 multiplied by.
Wait, isn't the first one positive 2? Oh, wait, no, I lied.
Mm.
Never mind.
The second is just 0. The third one is plus 2 multiplied by 12. Okay, now it's 22. Okay. So we can do another like along maybe
That's just like a trick.
Yeah. Along second column is exercise.